Hi, my name is Prakash Mitra, and this is Lab 3 Physics 2211 Black Hole and Orbits. Introduction. So, the purpose of this lab is to apply the principles of gravitation and momentum in order to determine the mass of the black hole. We also use these same principles in order to determine the orbit. Thus, our fundamental principles are gravitation and momentum. Preview. So the lab is split into two parts. In part one, we'll be using GlowScript in order to use a star's motion caused by a black hole in order to predict the mass of the black hole. In this, the system is the star and the surroundings are the black hole. We expect to have the mass of the black hole higher than the mass of the star in order for the star to keep in orbit. In part two of this lab, we use GlowScript in order to find an orbit for a spaceship that navigates both a planet and a moon and stays in both orbits. The system in this part is the ship, planet, moon, and the surroundings are nothing. We ideally expect to figure an orbit around the planet and moon, but if that can't be achieved, the orbit should at least be affected by both the planet and moon's gravity. In part one of the lab, this is my code. So the first segment, I calculate the initial and final momentums, and in the second component, I calculate the net force of the star. In the third component, I iterate through every second and append each mass of the star into a list. And in the fourth component, the last component, I draw arrows so it's visible when I'm running the code to see the arrows of the parallel, perpendicular, and net force. And on the right, we can see that I show all the constants. So for the gravitational constant, 6.7 times 10 to the negative 11. The mass of the star is 2 times 10 to the 30, and delta T is calculated appropriately. So as we can see, this is the results of the code, and we can see the orbit is complete. And in the first picture, we can see the orange arrow is the net force, the blue arrow is the perpendicular net force, and the purple arrow is the parallel net force. And the average mass I ended up calculating was 1.463 times 10 to the 34 kilograms. And this makes sense as the mass is greater than the mass of the star, which was 2 times 10 to the 30 kilograms. And this is my code for part 2 of the lab. So after tinkering around with the values, I found that the initial velocity in the x direction was 2 times 10 to the 4 meters per second, and in the y direction it was 2 times 7 times 10 to the 4 meters per second. And we can see that in the highlighted sections of code, in the first one I show that the initial velocity in the x and y direction. In the second one, I calculate the force of the planet on the moon. The third one, I calculate the net force on the moon. And on the fourth section, I calculate the force of the planet on the ship. Fifth one, I calculate the net force on the ship, and on the last one, I calculate the velocity and position of the moon and the velocity and position of the ship, and I update them accordingly using Newton's second law. And this is the result of that code, and we can see that it's not really a figure 8 orbit, but there's still an orbit around the planet and the moon for the ship, and there's also orbit of the moon around the planet. The blue circle represents the planet, and the magenta circle represents the orbit of the ship around the planet and the moon, and the cyan circle represents the orbit of the moon around the planet. And so some important distinctions to make is that the net force is greater as the two masses get closer to each other, and also the effect of the force of gravity was stronger on the smaller mass than it was on the larger mass. So what does this mean? So the question was, think about what the rate of change of momentum means, what net force means in terms of things you can observe and measure, and kind of showing the difference between this. So the momentum is defined as momentum equals mass times velocity. The rate of change in momentum is the change in momentum over the change in time. The momentum principle states that the net force is equal to the change in momentum over the change in time. Thus, there's really no difference between the net force and its parallel and perpendicular components and the rate of change in momentum and its parallel and perpendicular components, because they're expressed the same way. And so the what if question was, would there be any dominant interactions, or would they all contribute more or less equally in this imaginary system? So in my computation model, I would need to calculate the net force on the planet, moon, and ship with the black hole. I would apply Newton's second law to determine velocities, positions, and update them continuously. For the model to exist, the ship would need to have enough velocity to maintain orbit around all three other masses while not escaping or crashing. There will also be dominant interactions that would exist, such as the black hole and other large masses that exist, as those large masses increase the gravitational force that they impose. So a recap of my findings is that in part 1 of this lab, I found that the mass of the black hole was 1.463 times 10 to the 34 kilograms, and that the net force gets larger as the two objects get closer together. In part 2 of this lab, I found the velocity of the ship was 2 times 10 to the 4 meters per second in the x direction and 2.7 times 10 to the 4 meters per second in the y direction. and also that the gravitational forces of the planet and moon affected the orbit of the ship, which caused it to orbit unusually. And that's it. Thank you for listening.